Today we are going to solve our class A-level physics Cambridge system over there and physics paper 9702 with the code paper 2 variant 2 over there. In the start, I request you to the viewers kindly subscribe my channel and like the video and share the video with your classmates and friends over there so that whenever if you subscribe my channel, definitely you will when a new paper is being launched, easily notification will be available over there on your YouTube. Okay, and let's move towards our main topic over there, that is physics. It is A's level physics paper 2, A's level paper 2 variant 2, May June 2025. May June 2025 over there. Just recently, this paper has happened over there. I have just reviewed all the questions over there. Question number 1 was from dynamics, or we can say from the energy relations of kinetic energy, and a little bit uh, formula derivation of kinetic energy also over there. Formula derivation over there. And question number 2 was related to moment and pressure. Moment plus pressure over there was involved in question number 2. For question number 3, I will say that was related to waves, and that was related to intensity coherence over there. Intensity relation with amplitude over there was taken into account for calculating intensity of wave over there was included. In question number 4, I will simply say here that is that was related to elastic collision and force and momentum relationship. Elastic collision and force and momentum relationship over there. Momentum relationship over there. At number 5, I will suggest you that that was related to elastic deformation and elasticity over there. Elasticity, and it was related to little bit Young's modulus and energy related that. Young's modulus, and it was also related to a little bit about work done over there. Means energy stored in the form of elastic potential energy, like a work done with the help of graph question like that it was given over there. And question number 6 was there, which was related to electricity or DC circuits over there. That was related to electric potential and current to calculate in different components over there. Current over there. That was related to circuits, electric circuits over there. And number 7, the last question was related to fundamental physics of particles over there. Means I will say particle physics over there. Particle physics. So overall, if I observe here, by looking into the paper questions over there, in this term, in this paper, he has not included the physical quantities unit derivation over there. He has not focused like Doppler effect topic over there. He has not focused over there in which we can say too much related to kinematics or confusing things are not too much included in that paper. So overall, if I will rate this paper, I will say it was an easy paper. And if you want to make it easy, try to follow the steps which I have tried to solve this paper. Okay, let's move the paper now and let's go towards it. Let's check what it is happening over there. Okay, it is the paper is A level physics, 1 hour 15 minutes the time allowed for it, and it is May June 2025. Paper 2 variant 2. Structured questions are there, And there are total 7 questions with the parts. Total marks allowed is 60 marks over there. And every calculator, everything is allowed to you to use over there. Little bit formulas and values are given here in the form of insert. Let's move over question number 1 over here, where he is saying to us, okay, he is saying here, table 1.1, let's some physical quantities, identify with tick which quantities are vectors and which are scalar quantities over there. All right. So just look at here, acceleration is a vector quantity, displacement is a vector quantity, and gravitational potential energy is a scalar quantity, speed is scalar quantity, temperature is scalar quantity. Temperature is also a base quantity also there. Remaining displacement, speed, gravitational, everything is derived quantities over there. Scalar are those which have their magnitude and unit only, magnitude. And in case of vector, they have also the direction over there. So this was the technique how to go with the proper form of this part of this question number 1 over there. Okay. This was related to units of physical quantity, little bit a small part over there. Now he is moving towards kinetic energy formula derivation. A constant resultant force acts on a car of mass m. The car moves from rest, means its initial speed is equal to 0. And with constant acceleration A, acceleration is constant, mass, that is acceleration, that is initial speed over there. If I take both cases over there, then he is saying the car moves from the rest with constant acceleration along a horizontal ground. When the car has displacement s, the speed becomes v over there. So I will say here displacement displacement is equal to s, and acceleration and mass of car is m over there, and force was f over there, force f, and final velocity v. Force is f and final velocity is equal to v over there. What he is asking what to do using the concept of work done on the car, show that the kinetic energy of the car is given by the equation kinetic energy is equal to half mv square. All right, he is saying show the work done concept. As we know that work is equal to force applied F and multiplied by distance or displacement S over there. And we know according to Newton's second law of motion, F is equal to ma. So I am replacing this force F with ma over here multiplied by S over there according to W. So W, I know that it will become a kinetic energy over there. And if I use third equation of motion over there, that is 2as is equal to v square minus u square over there. In that case, I can say if I put my u as the initial velocity 0, it means u square is gone. And if I take from here my acceleration value, or what I need over there, a multiply s is present here. So I'm taking as it is, and then it will be as is equal to v square over 2. I'm replacing here a square by as by Vm into V square over 2. And then I can arrange this in the form of work over there, that W is equal to 1 by 2 mv square. And this work done can be given as a kinetic energy of this solution over there. So this was your formula derivation for this part over there. Let's move to the next over there. Here he is saying the mass of the car is 920 at time t is equal to 0. 920 kg is the mass. At 0, car is at rest. Okay, fine. When the time is 5.8, its velocity is 17 meter per second. Calculate the kinetic energy of the car at that point. Simply use the kinetic energy formula, which is equal to 1 by 2 mv square, which is equal to 1 by 2 into 9 to 0 into uh, speed is 17 meter per second, 17 square. Okay, just to calculate the kinetic energy there, I'm getting here 920, 9 to 0 multiply 17 square multiply 1 by 2, I can say divide 2. Divide 2 is equal to 13290. So 1132940. 2940. If I write it in the standard form, then I can say 1, 2, 3, 4, 5. Okay, 1.32. It cannot be rounded off over there. I'm giving answer up to one decimal place over there. Then it is 1.3 multiplied 10 raised to power 5 total joules over there. In the next part, let's see over there what he is asking now. He is saying when between the time t is equal to 0 and t is equal to 5.8, the work done against the resistive force is 4.7 multiplied 10 raised to power 4. Okay, it means that this is the last power over there. So we will have to go here to calculate the average output power of the car during the time. So I will have to use this energy also and the 1.3 10 raised to power 5, which was the previous value of this energy. I will have to add both of them because that is, even though that is lost energy against friction, but that is output power over there. So power should be taken with 4.7 multiplied 10 raised to power 4 plus 1.3 multiplied 10 raised to power 5 divided by the time is from 0 to 5.8. So I will have to take 5.8. Just look at the calculation over there. Fraction introduced. 4 bracket start 4.7 multiply 4.7 multiplied 10 raised to power 4 bracket close plus 1.3 multiply 10 raised to power 5 bracket should all be placed over here also. This one, and I am taking this bracket to this place to start the bracket over there. Okay, over 5.8. 5.8 equals to, in the form of decimal, 30517. 30517. 30517. I can write it 3.1. Okay, 3.1 multiplied 10 raised to power 4 watt over there. 3.1 multiplied 10 raised to power 4 watt over there. So this was the power calculation as an output over there. Now he is asking over there, at the time t is equal to 5.8, the speed of the car becomes constant. State and explain whether the output power of the car is greater than, less than, or the same as the output power just before 5.8 second. So I will say here that as he is moving with the constant speed, then I will say here at t point, t is equal to 5.8 seconds, kinetic energy is not changing. Kinetic energy is constant, and work is done against only friction. Work is done only, energy is provided only against friction over there. So no work is done to accelerate the car. No work is done to accelerate the car over there. The car, so output power is less. So output power is less. I think so. The concept behind it, you will be clarified now that the output power will be less now because no energy is being added with the resistive work done over there. Okay. Okay. Now he is saying define the moment of a force about a point. We can simply say here moment is we can also say that it is torque, in which we can say turning effect of force, turning effect of force about a point can be named as a moment over there. Or we can also say, according to formula, tau is equal to force multiply perpendicular distance of r over there should be taken to get the moment as a vector quantity. And if, for example, I simply give you an example over here, let's suppose it is a spanner which is being used to untie this nut over there. Then this is axis of rotation. Here you are putting the force and the distance between the axis of rotation and between the line of action of force. Then we can say it is the product of this perpendicular distance from the line of action of force to axis of rotation and the force applied is called moment over there. Okay. Let's move to the next what he is asking over here. A tree of mass 270 kg. Okay, mass is 270 kg, grows out sloping ground and is supported by a post as shown in figure 2.1. Okay, so the point which is shown as the rotating point over there, that is shown with the help of Q over there. The ground applies a total force R on the tree. Okay, total resultant forces are acting on the support with the help of R at point Q. Ground applies a total force R on the tree at point Q. This is the point Q over there. The center of gravity of the tree is horizontal to the distance 1.2 meter from Q. This is its center of gravity. Okay, the post applies the force F of 1800 perpendicular to the line PQ. So 1800 is the force which is perpendicular here, making a 90-degree angle, and 1800 Newton is being applied perpendicularly. All right, and it is 1.6 meter from Q over there. All right. Then what is he saying? The tree is in equilibrium and all the forces acts on the tree in the same plane. By taking moment about Q, show that theta is 20 degree. So I will say here, I will take clockwise moment and anti-clockwise moment. So moment due to weight, that will I say will be related to 1.2 meter is 270 kg and weight over there. Then I will say due to weight, the moment is moment, let's suppose I say moment M due to weight W is mg multiply perpendicular distance d, that was 270 into 9.81 into distance was equal to 1.2 there, 1.2 over there. And on the other end, the moment due to post over there, which is a support over there, post is there. Then if I go for it, then I will say here that its perpendicular distance can be given in the form of vertical height. This is given, if this is theta angle over there, then automatically I will say it should go with the with the base 1.6 and for the point P and the angle theta, this is going to this way, and I'm taking it 1.6 to be taken here and here. So I'm making an angle this point to this point. Okay. So my I will say perpendicular distance like that will be in the form of a base over there, and it will be 1.6 divided by cos theta. Okay. How I took this, I am taking here 1.6 into cos theta as a distance because this angle is being going to resolve its component, and 1.6 is this, and I need this angle in this side over there. Automatically theta should be taken and it will be 1.6 cos theta over there. So I am taking it, means cos theta ratio basically I used, that is base over hypotenuse, and my base is should be taken over there because that is given already. I need hypotenuse length over there, and that is base is 1.6 over cos theta I have replaced there. Okay, now I am taking here my weight was equal to 1800 Newton as a support force over there. So I am saying here 1800 multiply 1.6 divided by cos theta. So one is clockwise, another one is anti-clockwise movement over there. When he said to me in the question, there is an equilibrium, it means at equilibrium, clockwise and anti-clockwise moments are equal over there. So MW should equal to M of post over there. So 270 into 9.81 into 1.2 should equal to 1800 into 1.6 divided by cos theta. So I need cos theta. It should be shown over 25 degree. So I'm making cos theta as a subject. Cos theta is equal to 1800 into 1.6 divided by 270 into 9.81 into 1.2. Let's go for calculation. And now I am removing this cos theta with cos inverse over there. Okay. So I'm taking here theta is equal to cos inverse. Theta is equal to cos inverse. Let's go to the calculations over there. Introduce the cos inverse, shift cos, fraction introduced, 1800 multiply 1.6 multiply nothing. Come to the denominator over there, and 279.81. 270 multiply 9.81 multiply 1.2. 1.2, and bracket should be closed. Get the value. It is in radian. Okay, wait a second. I'm changing its setup over there. Shift. Wait. Oh, one computer is fine. Wait a second. I will have to go for degree setup first. Shift setup degree 3. Okay, now let's check. Shift cos inverse, fraction introduced, 1800 multiply 1.6 divided by 270 multiply 9.81 multiply 1.2, and bracket is closed, and you are getting your value 25 degree. So it is proved that the angle is 25 degree. So theta is equal to 25 degree over there. Okay, here he is saying that on the figure 2.2, draw a labeled scale vector triangle to represent the force acting on the tree. The weight of the tree has been drawn in this form over there. Oh, that is a very big figure, by the way. Here I will say that F can be labeled as F one force was F there and what one was R there. And I will say here that if I say weight is at the center over there and equilibrium is balanced and theta is 25 degree over here, 25 degree over here, then I will say here that it should be gone in this form with the help of use here the protector. Okay, the range will be given like 25, 26, 27, 28, minimum 25 should be there. So use the protector to draw this protector over there, and in the form of we can say it is the angle drawn from the tip over there, from the top of this point over there, that it is your force F. And on the other end, I will say here for R vector, we will have to go for R. R is drawn in the form of resultant R over there. R was normal reaction force. So it is round about 25 we have taken already. So if I take, then I will say that it is round about 37 to 40 like that on this direction. So it is R should be here, and it should be around, it should be 25 degree, and it should be taken as in the direction of anti-clockwise like this, and it should be clockwise like this, and its angle should be taken as the total is 25, and 25 we have taken, and the angle which he has given us over there in the form of theta. If I say that the ground is given over here and I'm trying to balance over there, then it will be around about 40, 37 to 40 like that. So it is 37 to 37, 38 degree should be used as its angle value over there. Okay. In the next one, he says that tree exerts a pressure of this at the top of post. Determine the area. So you have the force already given, that was, I think so, 1800. And we have known the formula of pressure is equal to force over area. And you want to calculate the area over there. So area is equal to force over pressure. So force is 1800 divided by pressure is 150 multiply 10 raised to power 3 there. Let's go with it. Here he is saying that 1800 fraction introduces better option. 1800 and divided by 150 multiply 10 raised to power 3 equals to 3 by 250. So that can be written as decimal form 0.012. 0.012 meter square is the formula area which is being exerted by the pressure over there. Oh, that is the waves. Okay, let's check over here. The progressive waves of X and Y. X is the smaller wave, Y is the larger wave, travel in a straight line from a point A to point B. The variation of displacement of the waves A at the instant are shown over there. Okay. State the amplitude of wave X. So amplitude should be taken from this point to the maximum point. The amplitude is in the centimeter over there. It will be 10 centimeter. It is 10 centimeter. Now he is saying both waves have frequency 16 hertz. Determine the wave speed of wave X over there. So for that purpose, we will say here, we will use the formula V is equal to F lambda. And if I see the wave X, then it is showing its complete one wave is here. It means this is its wavelength measured in meters. And meters is measured, so it is 0.4 meter. And I will say that is wavelength. Okay, 16 hertz is already given. 16 multiply 0.4 and 16 for the 64. It will be given as 6.4 meter per second is the speed of the wave. After that, he is saying state and explain whether X and Y are coherent. If we just observe here that they have the constant phase difference of 180 degree. This is upper positive, this is lower negative with the same frequency also. So we can say as X and Y have the constant phase difference, as the wave X and Y have constant phase difference of 180 degree like that. So they are coherent over there. So they are coherent over there. Okay. Let's check what he is asking in the next. He is saying here, wave X and Y superpose to form a resultant wave. Okay, sketch and variation. So there will be a little bit difference over there. And it will be having the 50%. Like if I observe the original wave, that it is 20. Okay, total for wave Y, the amplitude is 20. 20 is going on and cancelling the effect and making it 10 again, but it will be going in this form. So negative sign will be used for it, and we will be going to draw this. It will be like this form and this form, and then going up, then coming down. Wavelength will staying the same over there because they are superposing to give the resultant amplitude over there. So this is the way how to go with it. Okay. In the last, he is saying the intensity of wave X is Ix and the intensity of wave Y is Iy. Okay, you know that intensity is given by the relation intensity is directly proportional to amplitude square over there. And for that purpose, we introduce a constant and amplitude square over there. Here I will also say Ix over Iy will be taken as K A square, Ax square over K A Y square. So K cancelled already. Ax square. X was having amplitude how much? That was 10 over there. So it is 10 square over 20 square, which will equal to 100 over 400. Zeros gone. 1 by 4, 0.25. Or you can write 1 by 4 as the ratio over there. Okay, then he is moving towards question number 4 over there, where he is discussing a small ball. Is dropped from the rest from height h1, okay, above the ground and falls vertically downward, okay. The ball collides with the ground and bounces back vertically upward, okay, h1 height, and the ball collides with the ground and bounces back vertically upward, reaching a maximum height h2. Okay, and figure 4.1 shows that ball just before and after hitting the ground over there, and okay, 0.25 kg, and mass is the same with the speed which is it falling over there is 5.2, and the speed with which is bouncing back is 3.6. He has also changed the direction over there after bouncing back. The ball has a mass of 0.25, and in contact with the ground he is 0.18 second. Just before the ball hits the ground, it has the speed of 5.2. Just after, it has 3.6. Air resistance acting on the ball is negligible. State and explain whether the collision is elastic. No. Why no? because I will say here that kinetic energy is changed, speed is changed. So some energy is lost over there. As we can say the kinetic energy decreases because speed is decreased over there. So Coulomb is inelastic. So Coulomb is inelastic over there because speed is decreased, kinetic energy is decreased, because kinetic energy has the formula as half mv square, and this v value is decreased. Definitely kinetic energy is directly proportional to square of velocity over there. Then we can say it has decreased over there. Now he is saying calculate the change in momentum of the ball during the collision with the ground. Okay, so we will have to use momentum here. Momentum is a change in momentum. Basically, I know that it is mv minus mu over there, change in momentum. But here I will say the direction has been changed. So both should be added because u is, if I say u is negative over there as a larger value, then it should be having mv plus mu as direction is changed after bouncing back. So m is taking common, v plus u over there. M was how much? 0.25, 5.2, and 3.6. So I will say here 0.25 into will be taken as 3.6 plus 5.2 over there. Let's go for its calculation over there. That is 0.25 bracket start 3.6 plus 5.2 over there bracket close equals to 11.5, which is equal to 2.2 kg per meter per second square over there, meter per second. Determine the average force of the ball during the collision. So for calculating the force over there, we know the formula of relationship over there. F is equal to mv minus mu over t. This is rate of change of momentum is equal to applied force over there. So as I need here the average force, so I will say 2.2 divided by the time which was he's saying in contact over there, that is 0.18. Okay, 0.18. Let's go for calculation. That is 2.2 divide 0.18. Wait a second, 2.2 it was. 2.2 divide 0.18 equals to this equals to 12.222. So it is 12 Newton like that. Okay. Now he is saying calculate the height. Okay, it means I need height over there now in the form of ratio. All right. I will say here that I will go for calculation of heights to be achieved. Okay. I say let's go with the kinetic energy relation of mv square is equal to mgh1. Also go with the and use here velocity v1 square. Let's suppose we take here 1 by 2 into m. I'm just using because both are sides. They are cancelled out. They are cancelled out. Okay. And v square I'm taking 5.2 square, and with also going to divide it with 9.81 is to give me h1 over there. And height h2, it means the same relation I should use over there. H2 is equal to 5.2 square now. So I will take here 3.2 square over 2 into 9.81. Okay, and then I will have to go for ratio. Okay, we will go this H2 answer in the numerator and H1 answer as denominator over there. All right. 5.2 square divided by 5.2 square divided by 2 divided by 9.81 equals to this equals to 1.37 over there. 1.378. Okay, 1.38 is fine. 0.38 is fine. As meters, I will say here meters. Okay, let's go for 3.2 square. Just added 3.2 square here. 3.2. 3.6 it was. It was 3.6 by the way. So I should go here with 3.6. 3.6 square. So it is this, it is 0.66. 0.66. Let's go with 1.38 divided by 0.66. Then I will get H2 over H1. H2 over H1. Wait a second. I will have to change the values over there. 0.66 divided by 1.38. 0.66 divided by 1.38 divided by 1.38 is equal to this equals to 0.4784748 0.48 over there. So this was your question, which was related to much more simplified form of elastic and inelastic collisions to be discussed, and force and momentum relationships were used over there. Okay, now he is going towards question number 5, where he is saying define the Young's modulus, the ratio between stress and strain in an elastic body is called Young's modulus. According to its formula, F over A is stress over change in length over original length, which can be written as F multiply L naught over delta L multiply A. So this is the overall Young's modulus formula over there. After that, he is saying over here that a wire of unstretched length 0.81 meter, that is L naught. So L naught is equal to 0.81, and a metal with the Young's modulus 95 gigapascal, means it is the value of Y as a Young's modulus is 95 giga 10 raised to power 9 it is. And the obeys the Hooke's law, and a constant cross-sectional area of force and extension graph is shown over there. All right. Along extension is in millimeter and force is in Newton. Okay. Find the cross-sectional area of the wire over there. Okay. If we just observe here extension, I'm taking here 4, and the corresponding value here I'm taking 500. Okay, so my overall data, if I will write it for finding my cross-sectional area, I know the formula is Young's modulus is equal to F multiply L naught over change in length multiply area. So area is equal to F multiply L naught over delta L multiply by Young's modulus Y, or capital E also be used over there. Okay, F was 500 Newton. We have just checked over there, 500 Newton, and extension is 0.4 millimeter. It is 4 multiplied 10 is power minus 3 should be taken over there. Then I will say here that it is 4 multiply 10 raised to power minus 3. This is delta L value. And our Young's modulus was 95 gigapascal. Multiply 95 multiply 10 raised to power 9. And our original length was equal to 0.81. Is taken as 0.81 over there. Let's go for calculations over there a little bit. So it is fraction introduced, 500 multiply 0.81 come to denominator, 4 multiply 10 raised to power minus 3 and also go with multiply 95 multiply 10 raised to power 9. 10 raised to power 9 over there. Let's check what is the answer. That is 1.1, 1.06, 1.06 multiply 10 raised to power minus 6. So this is the area should be taken for the cross-sectional wire over there. Let's move. The extension of the wire is initially extension of the wire. So we will say here that it is taken in the form of our value as 2 millimeter, or that is delta L, or we can say it is extension X, 2 multiply 10 raised to power minus 3. All right. Determine the work done to increase the extension up to 3 multiply 10 raised to power minus 3. Okay. So I can use here both of these values to correspond their force value up to 2 and 3. 2 centimeter is having its value here as this is for 2 over there, and 3 is going to show here its value as here. So its value is for 3 extension, from 2 to 3 extension. So if I take the big triangle area and I go with 1 by 2 fx, okay, I am going with 1 by 2 multiply f was for where it is 1 by 2 into f was 375 into 3 multiply 10 raised to a minus 3 should be subtracted with the smaller area 1 by 2 into 250 into 2 multiply 10 raised to power minus 3. Okay, let's go and check what is the value over there. How much value we are getting over there. Fraction introduced. No need, I think so. Fraction over there. 375 multiply 3 multiply divided by 2 equals to this, equals to 562. 562 multiply 10 raised to a minus 3. So I can take it 0.562 minus 1 by 2, 250, and 2 multiplied times power minus 3. Okay. It is 250 multiplied by 2 divided by 2. It is 250 again. 250 multiply 10 raised to power minus 3. So it is 0.25. 0.56 minus 0.25. 0.56 minus 0.25 equals to this, which is equal to 0.31. 0.31, that is in the form of joules energy over there. This is the elastic potential energy which is present over there, and we will have to take into account to all of these values into the simplified form. So always whenever this type of question is coming, don't get confused. Try to understand the statement what he is asking for that question over there. Then I can say it can easily be solvable over there. Okay, this was your question number, I think so, 5 or 6? 5 it was. Okay, now we are moving towards question number 6 there. Define electric potential difference over there. So electric potential difference, we will simply define here energy transferred to the component to the resistive component, or like that, to the component, energy transfer to the component per unit charge. Per unit charge is called electric potential difference across the component over there. After that, he is saying a circuit contains 4 resistors and a battery. Okay. Electromagnetic force 8 volt. EMF is 8 volt. And with the negligible resistance, when the variable resistor has resistance R and the current in the circuit is 0.30 ampere I1, 0.30 ampere, and I2. The current in the circuit is 0.030. Okay, this is this one which is coming into the circuit and being divided into I1 and I2 over there. I1 and I2, both the currents are given. Then we can say here they are being distributed and divided. And we can simply say here that both should be given over there. Okay, just looking at this circuit over there now, let's move to calculation. Determine the charge passing through the battery in 4 minutes. So current is given. Just use the formula Q is equal to IT. So Q is equal to IT over there. I is your value with the 0.03. Okay, 0.03 into 4 minutes. So 4 multiplied by 60 over there. Let's go for simple calculation. It is not too much difficult. 0.03 multiplied by 4 multiplied by 60 equals to 36 by 5. It is 7.2 over there. So 7.2 Coulomb is the charge over there. Let's move to the next part. Calculate current I over there. So for I1. Okay. For I1, if we look here, that I2 is also given and I1 will be our value that this is the total because the voltage is staying same in the form of 8 over there. So 8 divided by both of these seriously, the resistor connected in series should be added. 430 plus 240 and will be equal to I1 over there. So I can say here 8 divided by 4 to 6, 3 to 4, 7, 670. Okay, let's do the calculator. 8 divided by 670. 670. Oh, 8 divided by 670 equals to this equals to 0.01. 0.011, it means 0.012. I round it off. 0.012 over there. 0.012. 0.012. 0.012 ampere is the current over there. For I2 we know that it should be subtracted from the total current 0.03 minus 0.012. 0.03 minus 0.012 and 0.03 minus 0.012 equals to this equals to 0.018. 0.018 ampere over there. Now he is saying calculate the resistance R. Okay, determine the resistance R. I will have to go. So I will have to go for variable resistor current. It should be taken. Okay, 0.03 ampere should be taken. So I will have to go for the resistance R, variable resistor. Okay, the current which is passing through this resistor 210 and this current is 0.018. And if I want to calculate the voltage drop across this resistor R, then I will say here I will have to subtract this because 210 and resistance R both are in series over there. Okay, so I am writing here, take the total EMF minus voltage drop across the resistor of 210 over there, 0.018 was the current which was in I2 over there, multiply by the resistance value was 210 210 divided by 0.018. This is the total current. If you just put all of these values in the calculator, you will get your resistance that is equal to 230 ohm over there. Okay, let's move to the last question, I think so now. No, it's still, this part is pending over there. Okay, here he is saying the variable resistor B is fitted with a scale so the resistance can be accurately determined. The resistance of 240 ohm is now replaced by resistor X. Okay, this one is replaced. X unknown resistance galvanometer is connected over there. With reference to the ratio of resistance, explain why this circuit has been used to determine the resistance X. Okay, that is easy, by the way. Here I will say when galvanometer reads 0, when galvanometer reads 0 reading over there, then we can say the ratio of upper resistance branch, the ratio of resistance in top branch, the ratio of resistances in top branch is equal to the ratio of resistance, the ratio of resistance in lower branch should be taken, and they will be equal, so the resistance of X can be determined. So the resistance of unknown resistor X can be determined over there. What is meant by fundamental particle? Fundamental particle. Okay. A particle, according to definition, I'm just explaining. A particle, fundamental particle like hadron, leptons, like that. A particle that cannot be divided or subdivided. Cannot be divided or subdivided into smaller particles. Are called fundamental particles over there. A nucleus X has 14 nucleons and p protons. Okay. All right. The ratio of the charge of mass to the nucleus of X is 4.1 10 raised to power 7 coulombs per kg. Okay. So for this purpose, I will say here the given amount for mass to charge ratio over there, then it is charge to mass ratio. Charge is taken with the help of one charge is electron, that is on the proton over there, will be multiplied by number of protons, that is total charge, to mass ratio. Mass is 14 nucleons, so it is 14 multiply. Mu should also be included over there, that having 1.66 multiplied 10 is for minus 27 kg should equal to 4.1 multiplied 10 raised to power 7. I think so. The concept how I manipulated this formula, charge to mass ratio having this value. So I need P over there. It will be 4.1 multiplied 10 raised to power 7 divided by 14 multiply 1.66 multiply 10 raised to a minus 27. And my E is also coming 1.6 multiply 10 raised to a minus 19 over there. Then if I get all of these into calculator, this is a big one. We should do it for one time. That is fraction introduced, fraction introduced, 4.1 multiply 10 raised to power 7 divided by 14 multiply 1.66 multiply 10 raised to power minus 27 multiply 1.6 multiply 10 raised to power minus 19 equals to what it happened. I think so I have made something wrong. Oh shit. I will have to take this 14 and this one in the numerator. Okay. I am cutting it from here. I am taking it 14 multiply 1.66 multiply 10 raised to a minus 27. Okay, just added these values a little bit over there. 1.6 10 raised to a minus 19 will be in the denominator. It's fine. Okay. It should be removed from the denominator. Okay, now come multiply by 4 multiply 1.66 multiply 10 raised to power minus 27 over there equals to 5.95, which is approximately equal to 6 over there. Okay, here he is showing X. Okay, it is beta negative decay over there. It means if it is 14 and this proton is 6 will be coming here, and beta negative is coming as a decay. So beta negative will be coming with minus 1 here down and 0 up, and some anti-neutrino particle should also be released, and it will be 0 0. And this, when beta negative is going to happen, its atomic number is going to increase by 1 and 14 over there. Here he is saying a sample of radioactive substance emits particles that positively charged and have a continuous range of kinetic energies. State and explain whether the nuclei in the sample are undergoing alpha decay, beta positive decay, or beta negative decay. So here I will say here that the nuclei are undergoing nuclei are undergoing to the beta positive decay over there, and this decay is showing that beta is going to beta positive decay for positive charge over there, and beta is positively charged. Beta is an electron particle, which is also named as positron, is positively charged. And he also said, explain whether nuclei go undergoing beta decay in case of energies over there. So beta charge. And in case of energy, I will say that beta has a range of energies over there. And alpha is having their values for discrete energy, but not range. Discrete energy, but no range over there. All right, this was our whole paper, which we have completed. This was May, June 2025. And students, kindly subscribe my channel. It is a request. What can I say more? Thank you so much for today. See you in the next paper. Allah Hafiz.